Let's take a look at an example dealing with a hypothesis test. So it was found that among 1,234 items checked by a store scanner, 20 of them were found to be overcharges. Now, before scanners were used, it was estimated that 1% of sales were overcharges, and we want to test the claim that with scanners, 1% of sales are still overcharges. So let's go ahead and highlight the claim that we're trying to test. So we're trying to test the claim that with scanners, 1% of sales are overcharges. So right away, I'm going to make a note to myself that we're dealing with a population proportion. So we're testing a claim about a population proportion, P, and then let's keep track that P represents the percent of sales that are overcharges, right, when we're using the scanners. Okay, so let's go ahead and write down this original claim in symbolic form. So we're going to test the claim that P is 1%. So you always write that as a decimal. And then let's go ahead and write down our two hypotheses. So that's the first step in hypothesis testing, writing down the null hypothesis and the alternative hypothesis. So if we take a look at the original claim here, notice that it contains the equal sign. That means that it automatically becomes the null hypothesis. P is equal to 0.01. And then I always tell my students to keep track of which hypothesis is the original claim, whether it's the null or the alternative. Okay, so then the next thing we do is we say, if this is not true, meaning if P is not equal to 0.01, then what are our options? Our options is that it could be less than 0.01 or it could be greater than 0.01. But we need a mutually exclusive statement. So if we simply say that the alternative is that P is not equal to 0.01, that means that it could be less than or it could be greater than. Okay, so with that in mind, I'm also going to write down here that since the alternative hypothesis contains the not equal sign, we're looking at a two-tailed test. Okay. All right, once you have the hypothesis written down, the next step is to write down your sample data. So what kind of information do we have as far as the evidence that we're collecting to test this claim? So out of 1,234 items checked by the store scanner, that's our N, our sample size. Okay, X here represents the number of items that were overcharges. So 20 of them were overcharges. So that gives us a sample statistic, P hat, a sample statistic of X over N, which is 20 over 1234. Write that as a decimal, that's 0.016. So here, our sample data shows that the proportion of items that are overcharges is, so that's approximately 1.6%. Okay, so 1.6% clearly is more than 1%, but the question that we want to ultimately do a hypothesis test for is to check to see, is it significantly more than 1%? So we see that it's different, right? It's different from 1%. In fact, it's more, but is it statistically significant? Meaning, is it significantly more? So to do that, we're going to have to calculate the test statistic for this p hat, and then we're also going to have to calculate the probability, which is the p-value. So let's go to the next slide here and do that. So in our next slide, let's go ahead and calculate the test statistic and the p-value for our sample data of 0.016. Okay, so we use this sampling distribution below here, and our P naught value, which is 0.01, is always in the center. And then these values here represent your z-scores, okay? Or you can think of them as your test statistics. Okay, so for this particular problem, our test statistic is going to be a z-score. So you can either use the formula or you can use your calculator. I'm going to use the formula first, and then I'll show you how to do all of this on your calculator. So the formula calls for our p hat, which is 0.016, minus our p naught value, which is 0.01. And we divide that whole thing by the square root of our p naught, which is 0.01, times 1 minus p naught. Divide that by 1234, which is our sample size. And if you're putting this into your calculator, I would use parentheses to maintain order of operations. And that gives us a test statistic or a z-score of 2.11. Okay, so I'm going to use green here, and I'm going to plot I'm going to use green here. I'm going to plot my test statistic on this distribution below. So that's a little bit over 2. So 2.11 is our test statistic. Now I need to define in here my critical value. So real quickly here, let me define my critical value and my critical region. And to do this, I need alpha, which we said in this problem, we're using an alpha level of 0.05. And since we have a two-tailed test, I'm going to have to split alpha in half. So that gives me an area of 0.025. So let me shade that. Well, let's go ahead and get the critical value. So the critical value is z sub alpha divided by 2, z sub 0.025. So on your calculator, you can use inverse norm here and just type in 1 minus 0.025, comma 0, comma 1, and that's going to give us a critical value of 1.96. Okay, and so 1.96, I'll use red here, is approximately here. So 1.96, and then let's go ahead and define it on the left tail since this is a two-tail test. So 1.96 is approximately here. So negative 1.96 is there. And then let me highlight my critical region. So in red there is our critical region. Now notice that our test statistic falls inside the critical region. So if you're using the critical value method, we can make the conclusion that, so here we can say since the test statistic falls in the critical region, we're going to reject the null hypothesis, okay? So the reason why we reject the null hypothesis is because our test statistic, so this 2.11 is the z-score for our p-hat of 0.016. So we're saying that the proportion of sales that are overcharges is different from 0.01. In fact, it's more, and it's higher, and it's statistically higher, okay? So it falls in that critical region, so we know that it's actually much different from 0.01. Now, if you're using the p-value method, so let me put that up here, the p-value method, then we need to calculate the probability of getting a test statistic that is at least as extreme as the one that we got, and the one that we got is at 2.11. So that's the definition of a p-value. So a p-value is the probability of getting a z-score that is higher than 2.11, so bigger than 2.11. So in your calculator, you can use normal CDF for this, normal CDF, and then you would type in 2.11, comma, and then I need more space here. So you would type in 2.11 as your lower limit, 1E99 as your upper limit, 0 and 1. And then let's calculate that probability. So on your calculator, that will give you approximately 0.017. So that tells us that this area in green, right, so this area in green here has a probability of 0.017, but then we also have to shade in that same area on the left. So I'm going to mark negative 2.11 here in my diagram, and then that area that's shaded in green is also 0.017. So together, if we add those two areas together, that gives us our p-value. So our p-value is equal to 0.017 times 2 because it's the total area on both tails because we have a two-tail test here. And so if you put that into your calculator, that gives us approximately 0.035. So here, if you're using the p-value method to make a conclusion about the null hypothesis, I'll write it on the left here, you would say, since the p-value, okay, is less than the significance level, okay, so we can see here that 0.035 is less than 0.05, right? Then we would also come to the same conclusion. We'll also reject the null hypothesis, okay? All right, so the last step is to now, so this right here, that's step 5, is making a conclusion about the null hypothesis. And then your last step is to interpret these results. So let's interpret that conclusion. So keep in mind here that the original claim is the null hypothesis, and we just rejected the null hypothesis. Therefore, we would make the statement, there is sufficient evidence to warrant rejection of the claim, and this is the original claim, that the proportion of items overcharged is 1% of sales. Okay, and we can actually say, in fact, our data show that the rate of overcharges has increased, right, to 1.6% with the use of scanners. Okay, and so next I'm going to show you how to do this on the calculator. So here you can use the calculator to get your test statistic and your p-value to help you come up with the same conclusion. So on your calculator, you're going to go to Stat. So you're going to press Stat, and then you're going to choose the third tab, Test. And here you're going to choose one proportion z-test, right? One, because we're looking at one sample, one population. Proportion, because we're testing a claim about a population proportion. And z-test, because we're doing a hypothesis test. And because we're testing a claim about a proportion, we always use the normal distribution, which are z-scores. So it's going to ask you to put in all this information. Now, on your test, if you're using your calculator, I'm going to ask you to show your work. So to show your work, this is what you want to write down. You're going to write down that you use a one proportion z-test, and then write down, all right, what you typed in, because if you make any simple mistake here, I can at least give you partial credit. And then I know you can't see it here, but in black here, you're going to choose calculate. So when you press calculate, it's going to lead you to this screen here. So this screen here, notice that it gives you a test statistic that's very close to the one that we got using the formula. It's just off a little bit because of rounding error. So this is your test statistic, which is your z-score. And then right below it, this is your p-value. So the p-value is the probability, okay, of getting a test statistic of 2.19 or higher. And so you can see here that that probability is around 2.8%, very close to what we got using the formula. Okay, so that's how you would use your calculator.